Hello viewers, in this session we will start complex power series. So, we will see complex power series which will help us to explore the properties, the local properties of analytic functions even further. So, to begin with we will see power series, complex power series as an example of analytic functions, and later we will show that every analytic function can be expressed as a power series around its point of analyticity. Okay. So, we will make that clear in due course. So, firstly to begin with I will give a refresher on complex sequences and series. So, the definitions and some of the preliminary results in complex sequences and series are very similar to the results in the corresponding results in real analysis or functions of one real variable, real functions of one real variable. Let me first define complex sequences. So, complex sequences. So, what are complex sequences? A sequence, like in the case of real numbers, okay, a sequence of complex numbers, okay, is a function f from the set of natural numbers to the set of complex numbers. Okay. So, what that means is that assigned to each natural number or to each counting number, there is a complex number. So, there is a first complex number, a second complex number, etcetera, that we can talk of via this function f. So, that is a complex sequence. Okay. So, f of 1 is usually called the first term of the sequence, etcetera. Generally speaking, f of n is called the nth term of the sequence. Okay. So, we can also talk about convergence of the sequence like we do for real sequences. Okay. So, convergence. Okay. So, a sequence, a complex sequence in this case. Okay. So, a complex sequence a complex sequence, I am switching to the notation a n. So, to say what this a n is, this f can also be denoted by, so f of n is also denoted by a subscript n sometimes, okay, the nth term of the series. Okay. And usually when one writes a n in soft parentheses like this, that means the sequence f. Okay. So, that means this particular sequence f, whose nth term is given by a subscript n. Okay. So, a complex sequence a n is said to converge to a complex number L, if for each epsilon positive there is a corresponding n naught or n epsilon, let me say, in the counting numbers, such that for each n bigger than or equal to this particular n epsilon, okay. So, what happens is the absolute value, the modulus of a n minus L is strictly less than that particular given epsilon. Okay. So, the number L is called the limit of the sequence A n. Okay. So, this definition is very similar to the definition of convergence of a sequence of real numbers to a limit L. Okay. So, the only thing to notice here is that in case of real numbers, we considered the absolute value of a n minus L, where a n is the nth term of the series, okay, and we wanted that to be less than epsilon for every n greater than or equal to a particular capital N, okay, depending on epsilon. In this case, that absolute value is replaced by the modulus of the complex number a n minus L. Okay. So, apart from that particular difference, pretty much the definition is the same. Okay. So, we can use the modulus in modulus of a complex number in place of the absolute value for real numbers. Okay. So, for this that is the definition of convergence. Okay. Next, we would like to talk about Cauchy sequence. Okay. So, like in the case of real sequences, we have we can call a complex sequence Cauchy if a similar condition holds. Okay. So, here is the definition, a sequence. So, this is the next point, a sequence a n of complex numbers okay, is said to be Cauchy, excuse me, is said to be Cauchy if for each epsilon greater than 0, there is a corresponding n epsilon belongs to the set of natural numbers, such that for any m bigger than n epsilon and n bigger than n epsilon, okay, the modulus of the complex number a m minus a n, okay, the difference, the modulus of the difference like that is strictly less than epsilon. Okay. So, the condition for a sequence to be called Cauchy is very similar to the condition for real sequences to be called Cauchy, except that once again the absolute value in the case of real numbers is replaced by the modulus in the case of complex sequences. Okay. And once again, why is this Cauchy condition useful? Once again, I'll state that proposition here. Here is a proposition. A complex sequence is convergent, okay, to some number L if and only if it is a Cauchy sequence. Okay. So, this proposition which I am stating without proof is very similar to the real case. This proposition tells us that complex Cauchy sequences, okay, can be judged to be convergent without actually knowing what the limit is. Okay. So, just by considering the difference, the modulus of difference of terms eventually you can conclude whether the sequence is convergent or not. Okay. So, that is the use of this Cauchy condition. Okay. So, like you know from real analysis, and then we proceed to define complex series. Okay, this line. So, consider a complex sequence. Okay. So, let a n be a sequence, okay, complex sequence, okay, and okay, the formal sum, okay, a 1 or a 1, yeah, a 1 plus a 2 plus so on, a 3 plus so on, okay, is called the series sigma A n. Okay. So, that formal sum where you add all the terms in that sequence is called a series, a complex series. All right. So, this is very similar to once again a real series, and the series we have the notion of convergence of series. The series sigma A n is said to be or said to converge to the sum S if the sequence of partial sums S n given by. So, you consider the partial sums S n equals A 1 plus A 2 plus so on until A n, or more formally sigma j equals 0 through or 1 through n of A j. So, the sequence of partial sums like that, these Sns converges to the limit S. So, you consider the sequence of partial sums, and if this sequence converges to a limit S, you say that the series sigma A n itself converges to the sum S. In this case, one writes S is equal to sigma n, or I will use j, j equals 1 through infinity A j. So, that is the notation. So, in this case one defines or one writes S, that sum S like that. So, that is a notation for this sum S. If the sequence S n does the of partial sums does not converge, then we say that the series sigma A n also does not converge. And one can by splitting a complex number A n into its real and imaginary parts, one can conclude the following: sigma A n converges if and only if the sigma of real parts of A n, the real part of A n and sigma of imaginary part of A n both converge. That is just by splitting a complex number A n, the nth term in the sequence A n into its real and imaginary parts, and then that is used in the partial sums sequence, and from there you can conclude this proposition. So, this proposition, the proof of this proposition itself is not very hard. It is just splitting a complex number into its real and imaginary parts. So, we will now see some properties of series, complex series. So, firstly, if sigma A n converges, then the limit as n tends to infinity of the nth term in the sequence from which we are constructing this series. So, limit as n goes to infinity of A n has to be 0. So, so although I did not introduce this notation limit n goes to infinity A n. Okay. It is what it means in the case of real sequences. Okay. So, notice the definition for convergence. Let me go back. Okay. So, notice the definition for convergence. In this case, okay, we normally write limit as n goes to infinity of a n is equal to L, this complex number L. Okay. So, that is the notation like in the case of real sequences. So, the viewer might be familiar with it from real sequences, and we are using a similar notation for complex numbers. Limit as n goes to infinity of a n has to be 0 if sigma a n, if the series sigma a n converges. Okay. So, that is one, that I will call this as point 1. Okay. And the second of these is that there is a number m. Okay. So, I should say this is there is a real number m, okay, or even further I can say there is a positive real number m such that maybe I should say there is a non-negative, because it could be 0, there is a non-negative real number m such that the modulus of a n is less than or equal to m. Okay. So, whenever the series converges sigma a n, the series sigma n converges, the modulus of the nth term, okay, has to be less than or equal to m for every n belongs to. Okay. So, that has to hold for, there is a fixed number m for which modulus of a n is less than or equal to n. All right. So, this property is going to be used several times in the in this or the coming lecture. Okay. So, this is important, and then the proof of either of these is very similar to the corresponding proof for complex or real sequences and series. Okay. So, I will omit the proof. The proof is very simple. So, the viewer can treat it as an exercise. Okay. So, that is property 1, and then property 2, if sigma a n and sigma b n are both convergent, complex series, okay, then sigma a n plus b n, okay, or more generally sigma a n plus c times b n, okay, is also a convergent series. Complex series, okay, for any c belongs to c. So, for any fixed or for any c belongs to c, for any complex number like that, the linear combination a n plus c b n is also a convergent complex series, okay, whenever sigma a n and sigma b n are convergent. Once again, the proofs of these properties are very easy. Absolute convergence, a series sigma a n is said to be absolutely convergent okay, if the series of absolute values of the nth term, namely sigma absolute a n, okay, converges. Okay. So, and then by applying triangle inequality, one can show that suppose that one can show the following. Suppose that the real series, notice that the absolute value series, okay, where you take the modulus of the nth term and consider the series sigma modulus a n, okay, that is a real number, real series, okay, series of real numbers, okay, and suppose that that real series converges, okay, then you can conclude that then sigma a n converges. Okay. So, this property can be proved using triangle inequality on the partial sums, okay, and notice that this is also summed up sometimes as if a series is absolutely convergent, then it is convergent. Okay. So, absolute convergence means the convergence of the absolute values series or the modulus series, okay, in the case of complex numbers. All right. So, now the fourth property is the tests for convergence hold, okay, is about tests for convergence firstly. Okay. So, we can apply comparison test, okay, ratio test and root test and Cauchy's nth root test, okay, to test the convergence of sigma absolute a n or sigma modulus a n, and if sigma a n is convergent, sigma absolute a n is convergent, then sigma a n is convergent by the above, okay, by property 3, by what we have just said. Okay. So, since sigma absolute a n is a real series, we can use the usual comparison test, ratio test and the nth root test, okay, and then accordingly we can conclude, okay, if sigma a n is convergent. Okay. So, notice that in property 3, notice that if sigma a n is convergent, it does not imply that sigma absolute a n is convergent. You know of examples already in the case of real numbers. So, that very same example applies for complex numbers as well. So, sigma minus 1 power n by n, for example, is such a series, okay, which is convergent, but not absolutely convergent. All right. So, now we can proceed actually to define power series. Okay. So, power series. Okay. So, that was a really crash course, a short course on what complex sequences and series are. Okay. But since the viewer is already familiar with real sequences and series, okay, so one can immediately extrapolate what the corresponding things are for complex sequences and series. Okay. So, the power series for complex numbers though take an interesting turn. One can see some important properties like why the radius of convergence should be a particular number, okay, in the context of complex series more clearly than in the case of real series. Okay. I will elaborate this at an appropriate moment. Okay. So, for now I am going to define power series. Okay. A series of the form is called a power series, okay, around 0, okay, in the variable z. So, z is a variable and that is called a power series around 0. Okay. So, if you are wondering why it is called a power series around 0. Okay. So, like in the case of real numbers, a series of the form, more generally a series of the form. So, let me use C naught here, C naught plus C 1 z minus a plus C 2 z minus a squared plus so on, okay, where C i's belong to complex numbers, okay, is called a power series. Okay, around a, around the complex number a, okay, in the variable z. Okay. So, that is a complex power series, and we will see that under appropriate conditions, okay, sometimes these series converge. Okay. And firstly note that the first series, okay, if you have power series around 0, okay, so power series around 0, okay, for example, or more generally power series around A, okay, converges for one number at least, namely 0, okay, converges for z equals 0, okay, or power series around A converges for z equals A. Okay. So, the set of points where this series converges is at least non-empty. Okay. So, but more is true depending on the coefficients A naught or C naught in either of these cases. Okay. So, we will see what happens. Okay. So, firstly, the notice that the partial sums. Okay. So, the partial sums of this series. So, first let me call this series of type 1 and type 2. I have to keep going back to these two types. Okay. So, I will talk about type 1 and type 1 series, power series, and similar statements hold for type 2 series. Okay. So, here I am going to talk about this type 1 series, the partial sums of series 1, okay, are, what are they? They are S naught equals A naught, S 1 equals A naught plus A 1 z, okay, S 2 equals, I will just go until S 2 A 1 z plus A 2 z squared. So, actually they are all, the partial sums are all polynomials in z, okay, and the next best thing you can do to polynomials is sort of the infinite version of the polynomials, which are these power series, okay, A 1 z plus A 2 z squared, so on until A n z power n. Okay. So, a power series is said to be convergent, okay, at a point z naught, at a point z equals z naught if the partial sums, okay, S n evaluated at z naught converge, okay, to a limit. Okay. So, if for a fixed z naught these partial sums converge, then we say that the power series converges at that particular z naught. Okay. So, that is the convergence, okay. And then we will now see examples. Okay. So, like in the case of real power series, we have the following examples. Okay. The first one is the geometric series. Okay. So, what is the geometric series? This is 1 plus z plus z squared plus 1. Okay. So, we know by simple arithmetic that 1 minus z times 1 plus z squared plus so on until z power n is 1 minus z power n plus 1. Okay. So, 1 plus z squared plus z power n, which is the nth partial sum of the geometric series, okay, is 1 minus z power n plus 1 by 1 minus z. Okay. If of course, we need that z cannot be equal to 1. Okay. And so, since the limit on the right hand side, okay, of n goes to infinity of z power n plus 1 is 0, if mod z is less than 1. Okay. What we can conclude is that when mod z is less than 1, when the absolute or the modulus of z is less than 1, okay, the series, the geometric series sigma z power n equals 1 through infinity, okay, or 0 through infinity in this case, okay, converges, and it converges to 1 by 1 minus z. Okay. So, this term here up here, this term is, this tends to 0. Okay. So, this geometric series converges to 1 by 1 minus z when the modulus of z is less than 1. Okay. So, also sigma or z power n plus 1 diverges mod z greater than 1. Okay. And we know that, yeah. So, in summary, sigma z power n, okay, has two kinds of behavior. It converges to converges to 1 by 1 minus z when mod z less than 1, okay, and it diverges when mod z is greater than 1. So, we will not worry about its behavior at the point mod z is equal to 1, i.e., on the circle, on the unit circle in the complex plane, but what is important is that the geometric series behaves in the following manner. There is this disk, there is this unit disk, okay, there is this unit disk, okay, inside of which it converges, okay, and outside of which it diverges. Okay. So, everywhere outside mod z, outside the unit circle, mod z strictly greater than 1, it diverges. Okay. So, there seems to be a disk of convergence in this case, okay, and we will see that this is typical of any power series. What I mean by that is, we will see that there is a certain round disk in the complex plane, okay, in which given power series converges. Okay. So, that is the proposition that I am going to present. Okay. So, here is a theorem. Okay. To each power series, okay, sigma a n z power n, okay, there exists a corresponding r, okay, with 0 less than or equal to r less than or equal to infinity. What I, yeah. So, we will allow infinity to be one value of r, Okay. What that means is that R is unbounded, okay, called the radius of convergence okay, with the following properties. 1, sigma a n z power n converges absolutely for every z with modulus of z strictly less than r, okay. And if mod z is greater than r, okay, there is a different behavior. If mod z is greater than r, the terms of the series diverge, of the series sigma a n z power n diverge, okay, are unbounded, okay, and hence the series is divergent. Okay. So, this theorem, okay, so what it is stating is that there is the behavior exhibited by the geometric series is typical. It is telling that not necessarily the unit disk, but there is a disk centered at 0 for the power series centered at 0, okay, in which inside of which the power series converges absolutely, and outside of which the power series diverges, okay. And on the circle itself, okay, on the circle of radius r itself, the behavior of sigma a n z power n is not told by this theorem. Okay. So, what happens to sigma a n z power n is not predicted by this theorem. Okay. So, what is important is there is this number r, the existence of this number r. Okay, it could be small or it could be large, which is given in this bound. So, r can be anywhere between 0 and infinity. Okay. So, like I have already commented earlier, r can be 0. Okay. So, we have seen that the power series of type 1 or type 2 converge at least for one point, namely the center of convergence itself, namely 0 in the case of type 1 and a in the case of type 2. Okay. So, it could be 0, I mean that could be the set of convergent points for the power series, okay, and it could be as large as infinity. Okay. So, we will see some examples of where the radius of convergence is infinity. Okay. So, first we will prove this theorem. So, the strategy is to let R be the supremum of the modulus of all such z's, such that sigma a n z power n, okay, in absolute value. So, the absolute value series sigma a n z power n converges. Okay. So, geometrically speaking, okay, so if we know a bunch of points where around 0 where this series converges absolutely, okay, we are picking the z, such a z, okay, which is the supremum of all, I mean such a z whose modulus is the greatest if one exists, or if if there are many of these points, then we pick the supremum of this set of modulus of such numbers, okay, and that is the candidate for our radius of convergence according to the theorem. So, if the modulus of z is strictly less than r, okay, then since R is the supremum of this particular set above, okay, then there is a Z1, okay, such that modulus of Z is less than modulus of Z1 less than or equal to R, okay, and by definition of R, there is this Z1 such that this A n Z1 power n converges absolutely. Okay. So, the series sigma absolute A n Z1 power n converges and Z1, there is such a Z1 between mod Z and R, okay, by the definition of R itself. Okay. So, since R is the supremum of such mod Z's. Okay. So, for this series here, okay, we can say that now there is an m greater than or equal to 0, such that the nth term of this series, okay, is less than or equal to m for every integer n, okay, every positive integer n, or for every n greater than or equal to 0. Okay. So, this comes from the property that I have listed earlier for series. So, let me go back, allow me to go back here and point to this property here. Okay. So, if sigma A n converges, there is a this property says that there is a non-negative real number m such that the modulus of A n is less than or equal to m for every n belongs to n. So, I am using that property for sequences or series rather. So, the nth term is less than or equal to m for every n positive or n greater than or equal to 0. Then what happens is that the modulus of A n z power n is less than or equal to, okay, is less than or strictly less than modulus of A n times the modulus of z by z 1 power n whole raised to n times z 1 power n in modulus, okay. And I will club this A n and this modulus of A n and modulus of z 1 power n and use this star here to say that this is less than or equal to m times modulus of z by z 1 power n. Okay. And since, okay, by star, this is by star. Okay. So, since modulus of z is less than modulus of z 1, modulus of z by z 1 is less than 1. Okay. And so, this becomes a geometric series, I mean this becomes the nth term of a geometric series. Okay. So, since this is less than 1, sigma m times modulus of z by z 1 power n, okay, is equal to m times sigma modulus of z by z 1 power n, okay, converges. And so, by comparison test, okay, this real number is lesser than this real number in comparison. Okay. So, by comparison test, we can conclude that sigma A n z power n converges absolutely, right. This is less than this. So, this converges absolutely. So, we have proved part 1 of this theorem. Part 2 of this theorem asserts that if mod z is greater than r, okay, and suppose and if sigma A n z power n is convergent, okay, is convergent for, okay, is convergent for that particular z with mod z greater than r, okay, then there is, okay, then what we can say is that there is an m greater than or equal to 0 such that the modulus of A n z power n is strictly less than or equal to m for every greater than or equal to 0. Okay, that is once again by the previous property. Okay. So, for any complex number w, okay, with modulus of z greater than modulus of w greater than r, okay, the modulus of a n w power n will be less than or equal to the modulus of a n. Okay, so, I will include the z power n here, okay, times the modulus of w by z power n, okay, which is less than or equal to by the above estimate, this is less than or equal to m times the modulus of w by z power n. Okay. So, it is a similar estimate to what we have done before in the previous case, okay, and since sigma m w by z power n is a convergent geometric series, okay, sigma absolute a n w power n is also convergent, okay, by comparison test. But notice that the modulus of w is greater than r, and we are saying that there is a number w whose modulus is greater than r, and sigma a n w power n is absolutely convergent. Okay. So, this is a contradiction to the definition of r. R is the, what is r? R is the supremum of all such modulus z, for which sigma a n z power n is absolutely convergent. Okay. So, here sigma a n w power n is absolutely convergent, and modulus of w is greater than the supremum of all such things. So, this is a contradiction to the definition of R. So, this cannot happen. So, what cannot happen? That this is convergent cannot happen. Okay. So, sigma a n z power n is divergent, okay, divergent for mod z greater than r. Okay. So, that concludes the proof of this theorem, okay, and I will remark that a similar statement holds, okay, a similar statement holds for power series of type 2. What I mean by that is, there is a disk of radius r around the point A, inside of which the power series converges, the power series of type 2 converges, and outside of which the power series of type 2 diverges. Okay. So, that is the statement in the case of power series of type 2. Okay. So, we will conclude this session here.